My name is Amy Lansky. I'm a researcher in the AI lab at NASA Ames in California. And I'm very honored to be introducing the speakers for the very last invited talk session of this conference. All three speakers have something in common. They all work on the relationship, somehow the relationship between computers and the world outside computers. So we have a talk on natural language understanding, and a talk on vision and perception, and another talk on how we can use computers to protect ourselves, usually from other computers. So those are the three talks. And I'm going to start off by introducing our first speaker, Barbara Grosz, who I know personally. 10 years ago, I did something that all my colleagues at the time thought was completely insane. But I was gratified to know that Grace Hopper thought was a really good idea, which was 6 months after I finished my PhD in systems, I switched fields completely in computer science to AI. And those of you who are in systems know that people in systems would think that was a very crazy thing to do. Anyway, when I entered AI, I started in the AI lab at SRI, and there, one of my very first role models in AI was our first speaker, Barbara Grosz, and she was really a very important, powerful person in that lab, so that was a very good role model for me. At that time, I was a fledgling researcher, and so in AI, especially since I hadn't even done my PhD in the area. After that time, she moved on to become a professor at Harvard University, and she's famous for her work in natural language understanding. She was also one of the co-founders of the Center for the Study of Language and Information at Stanford. And she's a fellow of various societies, and in particular, she's currently president of my own society, the AAAI. Without further ado, Barbara Grosz.
I told Amy she wasn't crazy. I'm going to talk on work in two parts of AI, on work in planning and work in natural language processing in dialogue participation. The title says collaboration in it, and the work has been done collaboratively. The work I'll talk about today was done with Sarit Kraus, who's at Bar-Ilan University, and one of my graduate students, Karen Lochbaum. It grows from work that I did earlier with Candy Seidner, and I'll come back to talk about collaborative work more at the end. This slide exemplifies what I'd like to get around in computer systems, and I'll give you a minute to read it. The question here is not only one of building systems that can communicate in natural language, because I think that's really a small part of the story. The question is, what's wrong with Seymour's buddy here? When Seymour asks for information on single males and houses of a certain amount, his buddy comes back and says, well, the best I can do is give you the serial numbers of the washing machines in Poughkeepsie. I lived in Poughkeepsie one summer, and those two things have nothing to do with one another. That's what makes the joke, and what I'd like to see us able to do is to provide systems that can be more supportive of their users and become problem-solving partners with them. And I see the work that I'm going to talk about today is fitting into that mold. This next dialogue is an example of the kind of system we'd like to build. The network manager is a person. The network presenter, NP, is what the role the system is meant to play. And so we begin here with the network manager pointing out a problem, then making a suggestion in utterance 3, well, we need to replace it with a particular kind of switch. I didn't want to offend anyone, so I put in an abstract name. And then the network presenter says, volunteers information to help with the problem-solving process. Well, we can't just go ahead and do that step. Before we do that, we have to do something else. We then have, noted by context 2, with a little bracketing around it, a discussion of exactly how we're going to do the action that's mentioned in utterance 4. We then come back to going ahead with doing the diversion action. The bracketing here shows something much like block-structured programming, but it's in natural language. In fact, it turns out that the way we speak to one another has something in common with the structures that we use when we do programming, and one can ask which came first. But in fact, this structure wasn't noticed until some of the research I'm going to talk about today. I want also to point out that there's a big difference here between the kind of communication going on between the network manager and the system and what we typically know with so-called interface systems. The network manager, in this case, isn't a master just directing the network's presentation system as a slave. And one of the things that I think we want to get around in the systems that we build is this notion that there's a master in charge and a slave just trying to do his or her work. In the next couple of slides, I'm going to show you a similar kind of dialogue. Again, one of the things that we're aiming to do in our group, but here we'll actually see the interaction of graphics and natural language. So the system starts out, can we have the graphic slide, by putting up a display of a piece of a network and noting that there's a anomalous utilization pattern. And I'd like you, since we don't have two view graph projectors, I'd like you to try and keep this picture in mind. You'll notice that there's attention paid to perceptual organization. Things are grouped together in certain ways. There's a legend on the right telling you what the symbols mean. Now, in this case, it's symbols in graphics, not symbols in natural language, but we have some of the same semantics problems coming up. You'll notice one of the things that I'll also come back to at the end in this discourse, that this isn't just an AI system. This is a system that's going to require collaborative work across the areas of computer science. Network people helping us to get information about current utilization rapidly, being able to display things rapidly. If you look at utterances 3 and 5, you see information about past history. So we'll need database people able to get us information, historical information, out of databases quickly. The dialogue goes on, and having gained information from the system about utilization patterns, the user now asks if Middleton has any maintenance problems. What our graphic design system did first round on this was to put up this kind of diagram. Well, now what's odd about this is that the system has completely changed the way in which it decided to contrast types of components. So in the first slide, we had color distinguishing among the exchange types. Now we have shape. Okay. It makes for an odd discourse. Well, we went back to the system and it produced the second diagram, which is much more consistent with that one I hope you still have in your minds. From this, we see actually another lesson learned by our graphics researchers from our language community, and that's that just as the history of the dialogue is important for natural language, it's important for graphics. And I think this is a nice example of flow going. So there are people who say, well, you know, what do you need natural language for? I have a mouse. Well, even when you have a mouse, you might learn something from natural language. And besides, you have to say things back to people. And when you say things back to people, you need to take their cognitive abilities into account. You need to display things in the ways that will resonate with the ways we think, and you need to say things that are coordinated with what you show. A view of, a one-slide view of discourse processing. To give you some background for the work I'm going to talk about in planning, though we'll come back to discourse at the end. Remember that network dialogue that I showed you, and I showed you the bracketing that gave you two different kinds of context in which to understand the discourse. In fact, one of the things that we found out early on in doing discourse processing was that there were these breakdowns in discourse, much like in block-structured programming. I might say as a piece of history, Amy asked if I was going to talk about my history. When I first went to SRI, we were building a speech understanding system. That was the first round, not the second round. It was in the 70s. And they had found someone to do system design and someone to do syntax and someone to do semantics, and my job was the rest. This is the rest, and I highly recommend to all of you doing the rest. It's always interesting to go out there in the bog and find out what you can do. But it is challenging. What I discovered was that discourses broke down into these units, and that the ways in which we talked about things depended on the units in which they fell. So the little squiggly lines on the left there are meant to be sentences or utterances. That's the way the language structures itself. And I might add here that we have since found in the 1990s version of speech systems, looking at intonation, that when we speak, we indicate in various parts of the speech signal when we're starting and ending these brackets. So you might think this only applies to paragraphs and text. In fact, it also applies to the ways in which we speak. Unconsciously or subconsciously, we raise our tone of voice at certain points and lower it at other points. We speak faster and slower. So there's information in the speech signal itself about this bracketing. The middle of this, which I usually have to explain to audiences, but I know I won't have to explain here, is a stack much like we see in computer science all the time. It turns out that referring expressions, pronouns, expressions like the projector, the pen, the glass of water, work much like variables work in programming languages, that when you move into an embedded segment of the discourse, you have something much like a push on the stack. I won't talk about that today. It's another area of research that I've been involved in. What I am going to dwell on today is the intentional structure, because that's the piece that has needed the most work. If you look at the ways in which the text breaks up, it breaks up depending on what people are doing. And that's what we saw, in fact, in that first dialogue, and we'll see that again when we come back to it. When Candy Seidner and I started trying to work out a formalization that would support intentional structure so we could begin to build programs that would manipulate it, we started with the early work in, the current, then current, now early work in planning in AI, which was oriented around robots, single robots trying to get around in the world. And we discovered that that wasn't sufficient for modeling the kind of planning that goes on in language processing. That in fact, collaboration was inherent in discourse. And when you think about it for a minute, you can see why that is. If you and I each know exactly the same thing, there isn't much for us to talk about. So usually when we're talking, it's because we have to give information to one another, because we have different information available, we have different capabilities. I'm going to talk about what's written in black, but I want to just point out that there are other characteristics of collaborative activity. One I've mentioned already is that the collaborators are more or less equal participants. They may have different capabilities, but they're participating on equal turf. There isn't this master-slave relationship. Another more recent personal story, which I told at dinner last night, and people requested that I tell all of you. My secretary prepared many of the slides that come later. When he and the pronoun here is important, when he handed them off to me yesterday, he said, "You know, there's some kind of gender issue in your talk." Now, I've been Dean for Affirmative Action this year at Harvard, and so I'm rather sensitive to gender issues, and I got very worried, and I said, "Well, wait a second, Charlie, what do you mean?" And he said, "Men don't have problems with the master-slave relationship. Why would you want to get around that?" This is not male bashing. He is a male. He's an aspiring drama student. I was actually quite taken aback, though it reminded me, and perhaps we could go to the top of the next slide. It reminded me of when Candy Seidner and I started this work, and we said, as it said on the top of the last slide, look, folks, we can't do collaborative planning just by building on the plans of individual agents. And we would present this work, and most of the men in the audience would say, no, if you just think harder and work harder on formalization, it will all come out. So I was led then to try and find a simple example that would illustrate the problem. And since I work in AI, and everyone knows that in AI, Block's world is where it's at, If you can't give a blocks world example, then you haven't gotten down to the essence. So here's the blocks world example of why we need collaboration. These are two people building a tower of blocks together. Now we'll leave out for the moment that they had to communicate somehow in order to figure out what they were doing. The question is, what's their plan? And if you think you can model their plan in terms of the individual plans of the individual agents, I hope the bottom part of the slide will convince you otherwise. I don't know what that means, and I haven't met anyone yet who does. I will say that when I presented this example to other people in the field, they not only understood it, but they decided this was a very fruitful area of research. And this does, in fact, give me hope because they have all become much more collaborative. They publish papers together now. And I think that's really great because I think that's really what this field is all about. Okay, I want to move now to say a little bit about the way in which we're formalizing this. And what I'm going to do is to give you a high-level view of how the formalization works, and then there will be several slides that have a fair bit of formalization on them, most of which have a red markings in some places. I don't expect you to read all of the formalization. I tried to put enough English around it that you could read in whichever language you read faster, and you would still have the context, but I want you to have the sense of what's there. The basic approach we take is to adopt what's been called the mental state view of plans. Rather than looking at plans as just data structures, we look at them in terms of knowledge about ways to do things and intentions to do them, and we separate those two out. Okay. And in particular, we're going to say that for an agent, an individual agent, to have a plan to act, the agent needs to have knowledge of how to act, and we'll call that a recipe, ability to act, and intentions to act. Okay. So we'll allow an agent to have knowledge about how to do something without a commitment to do it. And to convince you that that's important, we probably all have knowledge of how to hijack a plane, but I would say most of us don't ever get on a plane intending to do that. And we'd like to distinguish that in the agents we build. To have what I'll call a shared plan, and that's the construct that we model collaborative planning with, we need to agree upon the way we're going to do things, and we need to add intentions that our collaborators will succeed in their acts. A short view of what a recipe looks like. This should look familiar to all of you. It's very much like work in programming language semantics. We need to talk about actions. We need to talk about timing relations among them. We need also to be able to talk about constraints on the agents. Can I have the next slide, please? But it's easier for me in a short talk to illustrate some of the problems that come up in modeling recipes by going to recipes we all know. This is the first recipe you'll see for roast suckling pig. It's from The Joy of Cooking. I left out most of the subroutine calls. At the bottom of the slide, so the top 2/3 of the slide is a partial recipe. The bottom of the slide is a complete recipe. This is from a cookbook for expert chefs, and it says, I'll give you the English translation, stuff with English stuffing and roast. So this brings up the issue of how much, when I say that you need to know how to do something, do I mean you need to know what The Joy of Cooking says, or do I mean you need to know what Le Répertoire de la Cuisine says? Well, that depends on whether you're doing the action or not. And when we look at collaborative plans, we see that there's a difference between what the agent actually doing an action needs to know and the information that someone that agent is working with needs to know. And I'll come back and point out to you where that arises in the formalization. We also need to distinguish among two types of intentions, and this is actually work that has gone on not only in AI, but also is now appearing in philosophy. So we take a lot from philosophers, and now we're giving them back something, and I think that's a nice example of interdisciplinary work also. So if you have only a single agent, you need only to worry about intending to do something, like my intending to write a paper. But once you have multiple agents, you need to worry about intending that certain things will happen. So I intend that my PhD students write papers. Now I have more control over what I intend to do than over what I intend that they do. And in fact, I'm responsible for doing all of the planning involved in meeting my own intentions too, but I can only assist them in their intentions that. And so I'll ask you to keep that contrast in mind when we look at the formalization. Okay. Just to give you a roadmap of where I'm going to try to go, again, very quickly, in order to do this modeling, we needed to define a whole number of new modal operators to represent different states of knowledge. And I want to say here that this isn't this isn't something that we're implementing by having a theorem prover run over a bunch of equations. You should think of this as a specification for a system, and I'll try and point out some of the difficult issues that come up in the implementation. Today I'll talk mostly about the multi-agent actions, but because those embed individual agent plans, I'll talk about those briefly first. So we're going to go, if you look at the bottom half, the single agent part, we're going to look very briefly at what it means for a single agent to have a complete individual plan to do something, and then a partial plan. And an important thing to keep in mind, and as we look at this, is that most often when we're doing things, we don't know everything in advance. That's true of research, but it's also true of the things we do day to day, and it's true of the kinds of things we want to do with computer systems. Okay, so we'll say that an agent has a plan to do, a complete plan to do something if he knows how to do it and either intends to do every sub-act involved. Okay, so if I have a plan to make dinner, either I intend to make all the courses or I'm going to contract out some of them. And I'm not going to talk about contracting out. In contrast, as I said, we're going to go quickly through these slides. In contrast, if I have only a partial plan, well, where does partiality come in? It comes in two places. I don't have a complete recipe. I may know how to make the main course, but not the dessert. I may know where to find some of the information on the network, but I may need that to tell me where to find the rest of it. The other place that partiality comes in is at the bottom of the slide, and that's that I may not have decided whether or not I can do some of the actions. So again, even if I know how to do something, I need to think about whether I can do all of the things that are needed. And if I can't, I may need to get help. The potential intention to operator here is something that interacts with a general agenda for reasoning tasks. And that's where the locus is in this organization for figuring out what you're going to do. Well, let's get to the heart of what we're trying to do, which is the plans of multiple agents. Okay. And I've noted here in red, and that's on the left, what I'd like you to pay attention to. What's the added complication when you have more than one agent? Well, first, the agents have to come to agree on how they're going to do something. So whereas for me to act, I just need to find a way myself, if you and I are going to do something together, if we're planning to take a trip together, we have to agree on whether we're going to go by car or we're going to fly or whatever. So we have to agree on the way we're going to do it. Even though I may not need to know the full details of how you're going to do your part, I need to know what you're going to do. And that gets to the second thing I've written up by number 1, which is that I need to know that you're going to commit to doing your part in order for us to do our part. Okay. Then the situation that holds depends on whether the individual sub-acts are group acts or individual acts. So let's say that we're making dinner together and you're going to make the appetizer, we're going to make the main course together, and I'm going to make the dessert. Then the appetizer and dessert fall into the single agent case. The main course falls into the multi-agent case. The difference between this single agent case and the single agent case with the individual plan is that now we need to agree, that is, you need to tell me and I need to know that you're going to do your part. And I need to be prepared to help you. And that's what line D means. The full group is committed to the agent's success. That's where the operator to intend that comes into play. I'm going to push that up a bit. In the group case, we now need not individual intentions, but recursively a shared plan to do this subact. So we have a shared plan to make dinner that has embedded in it a shared plan to make the main course. And again, we need the full group committed to the subgroup's action. This just shows you the formalization, and I've just underlined the important intention that, which is the intention that on the part of all of the members of the group, that the group succeed in doing the action. Okay. Now we move to the case that we were really after from the very beginning. So this is what we want. Everything else falls out from this. This is the partial shared plan of a group, GR, to do some action alpha. We have here both the complexity of partiality, they don't yet know all of how they're going to do it, and the complexity of having a group. So if you look at clause 0, you see the first complexity that comes from the group, which is the commitment to the action of others. In the clause labeled 1, we see mutual belief in the recipe and also the need to complete the recipe. And then in the core case, we see recursively mutual belief and commitment to others coming into play. At the bottom of the slide, I want to slide that up, we see again the unreconciled case, and this is really where much of the computational complexity comes in. And in order to illustrate that, I want to look at the hook in this schematic for where we do some of the reasoning. We need at this point to be able to decide who's going to do the actions and which actions they're going to do. And the potential intention that is placed on everyone's agenda to consider. But in fact, we have an added complexity here, which is that we need to be able to model group procedures for reaching consensus. We need negotiation protocols for members of the group to decide who's going to act and how they're going to act. And we need to be able to reconcile individually our intentions to act on our own individual goals with our intentions to act in service of the group. Research so far, and this I should say is not just within this formalism, but within the field as a whole, has given us some very preliminary algorithms for doing each of these processes. But there's a whole host of research questions that are asked or that have been left open about how to do this. We have the next slide. One of the questions that arises, and you've really just seen this, the veneer, is that what we're doing these days? The veneer of the formalization here, I hope just enough to tempt you into wanting to look further and to probe further in how one might implement this. But the question then is, well, how do we know that we've covered all the turf? And of course we won't know until we try to build some of these systems. But we can get an inkling from looking in a different discipline at an approach to understanding what in this case is called shared cooperative activity. And this is work that has arisen in philosophy in part in response to the demand for modeling collaborative activity. And Brotman raises 3 characteristics. He says that any cooperative activity, and here what he's calling cooperative is what we call collaborative. One is mutual responsiveness, which gets handled in the formalization you just saw through intentions that agents, on the part of one agent, that other agents will be able to act. The second thing he says is necessary is a commitment to the joint activity, and we saw that directly in the intention that the group be able to do its action. He mentions under that meshing subplans, and he has a lovely example. I suspect this happened when he was trying to repaint his house. His example is repainting his house with someone, and he says, well, you know, you don't really have a cooperative plan if you're going to paint it blue and she's going to paint it red. That comes out again in the formalization in the intentions that. And finally, you need commitment to mutual support. If I'm having trouble getting the paint up the ladder and we're working collaboratively, you're going to help me. This comes through in various axioms that we have developed for intending that. Well, I promised to come back to dialogues, and I will. This is the network management dialogue you saw before, and now we have enough machinery to explain how the embedded dialogue fits with the larger dialogue. The larger dialogue is part of a partial shared plan to do maintenance on the node. One of the constraints is that the agents mutually believe that the network presenter, that's the agent in this case, of the doing the moving of the traffic, knows where it's going to move the traffic to. The embedded dialogue is then about the shared plan that you see in box P2, which is getting to the state where that agent knows the node or has a satisfactory description of the node. So the embedding in the dialogue is derivative of the embedding in the shared plans. People who know me know that I wouldn't be giving a dialogue talk if the air compressor didn't appear. So this is the first dialogues I worked on were air compressor repairs. I learned about air compressors. We see the embedding here of two sub-dialogues in a larger dialogue. And in fact, this is one of the places where you can see some of the referring expressions coming into play. The two Allen set screws, pulling it off. How do you figure out what those referring expressions correspond to? But I've put this up here for a different reason, which is that the first sub-dialogue you can see as being part of a partial shared plan to make it the case that the agents know the recipe that they're following. So a different kind of knowledge precondition for acting, in this case not knowing what you're acting on, but needing to know how you're going to act. Well, you can put that up. I'm not going to say anything about it because Amy told me I don't have much time left. This is one application of this collaborative planning framework. As I mentioned in the beginning, one of my collaborators is Sarika Kraus, and she's not interested in the dialogue part, but in building computer agents that collaborate with one another. You can think of using this as well for information access and different systems going out over the network to find information. Crisis management where people and machines need to collaborate. And finally, and I think our next speaker will say something about this, robots collaborating. I'm going to put up a cartoon as the final slide. This has a message both for the research and for doing research. Let me just say that some of the current research problems include developing algorithms for intention conflict, for reconciling intention, for helpful behavior, and most particularly for elaborating and recipes and assigning agents to tasks, and for negotiation. I like Calvin and Hobbes. They tell us a lot about life often. Here we have the message about planning and acting being interleaved, and so they start out going on an adventure. You can think about doing that with your system or doing that in your own research. Can you read this? No? Okay. So Calvin says, ever notice how decisions make chain reactions? And Hobbes says, how so? Well, each decision we make determines the range of choices we'll face next. A third panel is, take this fork in the road, for instance. Which way should we go? Arbitrarily, I choose left. You'll notice that they're developing their recipe as they go along. They get to error correction a little later. Now, as a direct result of that decision, we're faced with another choice. Should we jump this ledge or ride along the side of it? If we hadn't turned left at the fork, this choice would never have come up. You'll see yet another lesson and another thing that we need to cope with, which is that sometimes you can't just undo what you did, unfortunately. I note with some dismay, this is now Hobbes, that you've chosen to jump the ledge. Right, and that decision will give us new choices, like should we bail out or die in the landing? Exactly, our first decision created a chain it's hard to learn sometimes. Created a chain reaction of decisions. Let's jump. No, leave that covered up for a minute. In order to get beyond Seymour and his buddy who wasn't very helpful, I think there's a lot of collaborative research to be done within computer science and across computer science and other disciplines that will give us systems that can work with users and that can incrementally develop plans and modify them. I think there is in this cartoon also a lesson for research life, which it is, as I think earlier speakers have said, an adventure. I hope you'll all go for it. I hope some of you will join us in building collaborative systems, because I think that really is where the future lies. I might note here that last night at the dinner, several people said they didn't understand why fewer women were entering computer science than previously. The message we get from many of our undergraduates is that they like to work together with people on things, and they think that what you do in computer science is work alone. You all know that's not the case, and I think it's the most important message to get across to high school kids, and especially high school girls, so that they'll join us in this endeavor. I might add here that I mentioned earlier, I guess in the last session, that I had worked on a report on women in science at Harvard. When that report came out, a significantly larger percentage of women coming to Harvard interested in the sciences dropped out than men did. That is, if you look at the incoming freshmen, 10% more women wound up not being concentrators in science than men did. We've now equalized that, and I give credit to the science departments that worked on their introductory programs, most of them introducing collaborative work. Project courses and things like that. And now you can take off the last slip, which is Calvin and Hobbes telling us about talks. He says, see, if you don't have each decision make each decision carefully, you never know where you'll end up. That's an important lesson we should learn sometime. And Hobbes says, I just wish we could talk about these things without visual aids.